Okay, so this is a lecture for the third week of October, and basically what we're going to do in this first video is complete the lecture on the mathematical expectation for random variables. So we already went through the material of the expectation for a random variable. We also discussed the variance and the standard deviation for random variables, and today we're going to look at the new measurement. This measurement is the covariance of random variables. And essentially, the covariance between two random variables is a measure of the nature of the association between the two. So we want to know how are these two random variables associated. Okay, so when you look at the covariance is a measurement of association. So definition 4.2 yields an expected value called the covariance of x and y, which we denote by sigma of x and y, or the covariance of x and y. So by definition, let x and y be random variables with joint probability distributions of x and y. Then the covariance for the discrete case is provided by this expression. Sorry, go back to the slide. So we have a definition for the discrete case and a definition for the continuous case. So for the continuous case, again, we look at the summation of the multiplications of the distances from the outcome of the random variable x to the mean times the distance from the random variable y to its mean times the probability of this event happening. And we sum that for x and y. For the continuous case, we do the same thing, but we look at the double integration. Okay. So again, the covariance between two random variables is a measure of the nature of the association between the two. The covariance is a measure of a linear relationship between the two random variables. And the sign of the covariance indicates whether the relationship between two independent random variables is positive or negative. So on the next slide, I'm basically showing you with this figure how are these relationships represented with the graph. So for example, when you talk about the positive covariance, every time you have a large value of x, let's say large value of x, so x is large, we also have a large value of y. That means that you have a linear relationship that is positive. So that means that the covariance of the relationship or the association between these two random variables is positive. On the other hand, when you look at the negative covariance, when you have a large value of x, you have a small value of y. And when you have a small value of x, you have a large value of y. That relationship is what we call in relationship that is negative covariance. Then there are other random variables that doesn't have this type of relationship or behavior. In those cases, we have zero covariance. And here in this figure, we have two examples in where this behavior is shown. Okay, so for this case B and D, you have a zero covariance. Okay, so again, if large value of x often result in a large value of y, or small values of x results in small values of y, the product of these two differences from the outcome of the random variable to the mean of the random variable for both of them will tend to be positive. On the other hand, if you have a large value of x and that results in a small value of y, the product of these two would tend to be negative. So you have a negative covariance. When x and y are statistically independent, it can be shown that the covariance is 0. Two variables may have 0 covariance, but still not be statistically independent, so the opposite does not apply. So if you show that both of them, x and y, are statistically independent, then you can also show that the covariance is 0. But if the covariance is 0, does not necessarily mean that the two variables are independent. Note that the covariance only describes the linear relationship between the two random variables. Therefore, if a covariance between x and y is 0, and x and y may have a nonlinear relationship, which means that they are not necessarily independent. Okay, so this is from your textbook. So theorem 4.4 says that the covariance of two random variables x and y with means mu x and mu y respectively is given by this expression. The expectation of both random variables x and y minus the multiplication of the two means. Let's look at this example. In this example, we have the fraction of x, which is our random variable, of male runners, and the fraction of y, of female runners, who compete in a marathon race, are described by the joint density function x times 8 times x times y, and for these ranges, and 0 elsewhere. And the problem is asking for the covariance of x and y. See if there's any association between these two random variables. So for this problem, we're going to use the expression sigma xy equals the expectation of x, y minus mu x times mu y. Okay? So the first thing we have to do is to find the marginals of x and the marginal of y. Marginal of gx and hy. Okay, but because the only thing we have right now is just the joint density. If we want to find the expected values for x and y, we need their marginals distributions. So that's the first thing we're going to do. So let's find the marginal for x. That is equal to the integration from 0 to x of x 8xy dy, and that equals 8xy squared divided by 2, evaluated from 0 to x. And this equals 4x cubed, and that's for x between 0 and 1. Okay, we're going to do the same thing for the marginal of y. So in this case, we look at the integration from 0 to y to 1 of xyj dx. And this should be equal to 4y times 1 minus y squared. And that's for y between 0 and 1. So now we have the marginals for x and y. So what we need to find out is what is mu x and what is mu y, okay, in order to get the covariance. So for mu x, we know that this is the expectation of x, and this will be equal to the integral from 0 to 1 of 4x squared cubed dx, and that should be equal to 4 over 5. For mu y, this is the expectation of y. This is the integral from 0 to 1 of 4y and I'm sorry, I forgot an x here. You need to multiply that by x. So here you have to multiply times y. So we have an extra y here times 1 minus y squared dy. And this will be equal to 8 over 50. So now we have the expected values for both x and y. The only term that we don't know is this one, the expectation of x and y. So for that, we can also find that using the material we learned from this lecture. We know that this is the double integral from 0 to 1 from y to 1 of 8x squared y squared dx dy. And if you solve that integration, you'll get 4 over 9. So finally, we can solve for the covariance. So this is equal to the expectation of x and y minus the multiplication of mu y and mu x, and that equals 4 over 9 minus 4 over 5 times 8 over 50. And this is equal to 4 over 225. So as you can see, this covariance, you solve this using your calculator, this will be very close to 0. So that means that there's a covariance of 0 or close to 0 for this relationship. So you can say that the fraction of male runners and the fraction of female runners are independent, or these two random variables are independent. Okay? So the covariance between two random variables does provide information regarding the strength of the relationship. Since sigma of x and y is not scale-free, its magnitude will depend on the unit used to measure both x and y. There's a scale-free version of the covariance that is called the correlation coefficient that is used widely in statistics. Okay, so the correlation is also another measurement related to the covariance and is used very frequently in statistics. And essentially what the correlation does is you look at the relationship of the covariance and the standard deviations of the independent random variables. So let x and y be random variables with covariance sigma x and y and standard deviation sigma x and sigma y respectively. The correlation coefficient of x and y is given by the division of the covariance by the multiplication of the standard deviation. Should be clear that the correlation is free of units of x and y, satisfy the inequality of -1 up to 1, and assumes a zero value when the covariance equals 0. So in summary, in this lecture, we covered the material on mathematical expectation, and this is chapter 4 of your textbook. And specifically, we discussed the topics of the expectation or the mean for a random variable, and also how to get the covariance and the variance of a random variable. The learning objectives were to calculate means and variance for random variables. Okay, so this finalized the lecture on mathematical expectation in this video.